We are very excited about working with Ignatius and CAWASA. This is a very special opportunity to help with your group and to bring our volunteers together, since we can't have them traveling right now. So thank you for joining us. A warm welcome for each of you to these courses. And I can see that we are eager to leap in, so I'm going to just take a brief couple of moments to, in case some of you aren't familiar with, we've been using Operators Without Borders. Well, what do we do, and who are we? So we've got two focuses with Operators Without Borders, which is a nonprofit, a charitable organization. We assist water and wastewater utilities to recover from disaster situations. So, for example, when the Bahamas utility reached out to us, we were able to send volunteers to work with their operators. And the second thing that we are doing is to help build capacity through training and mentoring water and wastewater operators. And guess what? The perfect example is today, as Mike is going to be leaping in and doing that very thing with you. So with that, I want to say that really who we are is operators helping operators with, of course, the people that are involved also with operators. That was a lot of operators in there. So that brings us to Mike Ippen, our wonderful instructor and facilitator. I've been given a bio bit, but I've known, as you could probably tell from Mike and I talking, I've known him for a long time. So I'm sure this bio bit is just kind of the tip of the iceberg. And if he wants to add anything after, he should do that. So Mike began his career as a utilities operator with the District of North Vancouver. He spent 6 years as deputy superintendent before moving to Saanich on Vancouver Island, which is more of a paradise than over here. He retired from the City of Victoria in 2017, where he was the utilities manager. Mike has served on the boards of the BC Public Works Association, BC One Call, and BC Water and Wastewater Association, serving a term as president of the BCWWA, that's Water and Wastewater Association, from 2015 to 2016, and as executive director of BC One Call until May 2020. Throughout his career, Mike has been an advocate for operator education, and I can certainly attest to that. He has been an instructor, developed curriculum, and delivered training across BC, Yukon, and Ontario across a variety of subjects, including public works leadership and administration, water quality and distribution systems, wastewater collection best practices, and water loss management, which is a really important one. Mike lives in Victoria with his wife, Stephanie, and when not teaching or facilitating public works and utility education, he writes novels and tends his garden. And I've read one of those novels and was found it quite compelling. So I can attest to that too. So I'm going to be leaving you in good hands with Mike, as I'm not able to, unfortunately, stay for the whole session. He'll be going over, as Ignatius said, how things work. But I was asked by Valerie Jenkinson to just mention this, although we may have had a spoiler alert. While we have you at the start and fresh and excited about all these things, we're going to start with a big adventure, and yes, it's called math. Because we know that it's a foundation and everything will flow from that in the weeks to follow. And of course, we all know also that numbers count. Sorry, Mike, couldn't resist that. And on that note, I'll pass you on to our #1 instructor, Mike Ippen. Take it away.
Thanks, Madeline. And thanks to all of you for attending. It is a bit of a letdown. I was an operator for 7 years in the field before I got my, I think I was about 5 years in the field as a laborer before I actually wrote my first cert exam. And I can remember just dreading the math because it had been, years since high school doing the calculations. And so, yeah, it's a bit of a bummer starting off with math. And the other part of this too is because it's an exam prep, my understanding is at the end of this program, 11, 12 weeks, you'll be writing your certification exams in either water distribution or water treatment, which is great. So once the groups split up, we'll have lots of content that should supplement the actual work you're doing every day as operators, either in a distribution system or systems or in a treatment plant. So this material is really meant to complement what you're doing, because the experience for a lot of operators, whether they're working in the United States or Canada or Australia for that matter, if, depending on the utility you work for, you could have a variety of tasks over your career, or you could get into a stream where you do only one or two functions. And I've known operators that have worked on fire hydrant maintenance for 25 years, or they were the supervisors in the meter shop, taking apart meters, recalibrating, testing, and doing all the admin around water meters. And so these courses really come in handy to round out knowledge that you wouldn't otherwise get in the field on the job. So having said that, you're going to find, some of you, that some material is going to be repeats of what you're doing. It might even be at a lower level than what you're doing. But the goal is for you to feel really confident at the end of the process in writing an exam. So that's what we're hoping for. And so that's how we're going to go ahead. And we've broken down a course that typically is a week of full-time classroom time into 11 or 12 weeks, which means some of the units we're going to spill over from week to week, because some of you may have heard me asking Ignatius. I'm going to try and keep it to 2 hours. So at 5 o'clock your time, it is 3:15 now. So 5 o'clock your time, we're shutting down. I've got an assignment that you may have already got. The idea is that you can work on that assignment through the week. We'll review it next week. If you don't get done, don't sweat it, because we'll review most of those questions, if not all of them, as a group, and then supplement it, and we'll work with assignments that way. Because as you know, working in water treatment or distribution systems, there's a huge breadth of information. And the best way to try and capture that in a 100-question exam can be difficult and challenging. So we want to hit the high spots and also make it so that you can feel comfortable writing the exam. So if you have any questions, because of the group size today, if you have any questions, just chat, send it through chat. I think I've got my chat line open here. And then I can try and answer them as we go, or I can send you back information along the way. So hopefully that's a good start. So let's get going. We're going to start with math, and we're going to start at the beginning of math. So for some of you, that may be actual arithmetic functions. So we're going to look at some calculations as well. You work in the metric system. We're going to cover off some of those units, conversions, percentages of the systems, how we use them, area volume calculations. You will get, I'm assuming that where you are, you will also get exam calculation sheets, so you don't have to memorize the formula. That's how it works in ABC in North America, so I'm assuming it's the same for you. However, we'll show you some of the basic calculations that you should feel comfortable doing, and where to look for the information as well, and how to solve for problems as they come up. And this is kind of the full range of what we'll look at today if things go well. As you know, as operators, math comes into it on a daily basis. Sometimes not as much for distribution system operators compared to treatment plant operators. However, one of the things to get operators more comfortable in the field and to really understand what they're doing is to feel confident about doing calculations as opposed to just reading a value off a drawing or a blueprint or a manual from a pump manufacturer or a meter supplier, is knowing how those values were reached and feel comfortable in being able to replicate that. And so we're going to look at some examples of math in the system, but you want to be able to feel like, okay, even if I don't have to do it on a daily basis, I know how to do it. So you think about where math comes in as an operator, whether it's reading plans, taking information off a blueprint or a drawing, calculating or totalizing flows from consumption, looking at discharge rates for pumps, looking at pressures and head calculations in the system, whether you're looking at a SCADA readout or actually attaching a pressure gauge to a fire hydrant. Let's see, yeah. So we sometimes use as a shortcut to doing the calculations this expression, bed mass. So you can see in red, it basically means do the calculation in the order of bed mass. So brackets first, then exponents, then division and multiplication, and then addition and subtraction. And the reason we do that is if you do it in the wrong order, you can get the wrong result. So what seems like a straightforward calculation, and you might, you know, win a lottery and there's a skill testing question at the end and there's always 10 different calculations. Do them in the wrong order, you get the wrong result, you lose the money. So it's really important to do it the right way. So on the screen is an example. 3.4 plus brackets 6 divided by 2 times 4 squared. So in red, the wrong order is just doing it from left to right. If we look at 3.4 plus 6, and then that equals 9.4, we divide that by 2, that's 4.7 times 4 is 18.8. No, that's not how it works. The right order is right brackets. So 6 divided by 2. Solve the brackets first. All right, so that's 3. So now our formula is 3.4 plus 3 times 4 squared. Okay, well, we don't want to do the addition yet. The next calculation to solve the problem is exponents. 4 squared, so that's 4 times itself, right? 16. Now we have 3.4 plus 3 times 16. All right, multiplication is next. 3 times 16 is 48 plus 3.4. So be comfortable in doing the calculations in the right order. You can see 51.4 is very different than 353.44. And if that was a dosage calculation or a feed rate calculation, we have a problem if we're going to use the wrong value here. So that's just one example. Always do the solve for the unknown in the right order. Brackets, exponents, division, multiplication, addition, and subtraction. Okay. Metric system. Let's see. Yeah. So metric system, we use metric units. So our basic measure of length is in meters, mass or weight is grams, volumes liters, pressure in pascals, but because those units are so small, we typically deal with kilopascals, so by the 1,000, and temperature is Celsius. Pretty straightforward. The metric system, these are, I think you have this handout, so you can take a look at this on your own time as well. Pretty straightforward, but basically because everything is multiples of tens and hundreds and thousands, we either have more, so higher than the decimal point, or below, so micro and milli and centimeters, decimeters, and then once we hit meter, then goes the other way, right? Deca, hecto. The one we typically use is kilos, so kilograms or kilometers, kilopascals. So be familiar with that. You don't have to memorize these, but if you're working in the metric system, it helps to be comfortable with what the prefixes are actually representing. And we're going to go over in a little more detail some examples with specific units. As operators, there's lots of opportunities for us to have to convert units. We either have to do it because there are no tables or calculations available. We're doing it on the fly in the field. And we need to be able to set up our ratios like fractions with a numerator and denominator. And really what we're talking about is being consistent with the proportion between the values. Okay, so when we're looking at a ratio, it means if we want to know the relationship between 1/2, 1/2, to 4/8, when the numbers are small and fairly common, we can do it in our heads very easily. But when we start getting decimal points or very large numbers and values, sometimes it's confusing to know where the units are placed. Are they above the line, so the numerator, or below the line, the denominator? So here's a couple of samples. If we've been asked to convert 3.2 kilometers to meters, we're all working within the metric system here. We know that 1 kilometer is 1,000 meters. So in our heads, we can quickly do that. Okay, so that's 1,000 times 3.2. But to actually set it up, we're looking at, okay, the relationship, the ratio between 1 kilometer to meters. Well, 1 kilometer is 1,000 meters. So there's our numerator, 1 kilometer, 1,000 meters is our denominator. We are asked to convert 3.2 kilometers, so our known is the numerator, 3.2 kilometers, because it matches the units on the left-hand side of the equal sign. So how do we solve for the unknown? Well, we already know it's 1,000 times 3.2. And we can see that by doing the cross multiplication. We bring the 1,000 meters up times 3.2 kilometers. And if I had a chalkboard, we'd actually be cutting out or eliminating, canceling out the kilometers above the line. Anything above the line is canceled out to below the line. So we end up with 3,200 meters. But it's all based on knowing how to set it up. So if we were ever in a situation where the numbers aren't that clear, like in the following, converting 390 kPa to PSI. So we're going from metric to imperial. 1 PSI, we know, and our tables will show that, is the equivalent to 6.9 kPa. So we now look at 6.9 kPa is to 1 PSI below the line, as 390 kPa is to what? All right, so now what we're going to do is we're going to multiply. We bring the 1 PSI up to the top of the line. 1 PSI times 390 kPa divided by 6.9. The kPa values or units vanish, and we divide that 390 by 6.9, and we end up with 56.5 PSI. We've changed the units because the kPa above and below the lines are canceled out. So that way we get to the unit that we want and the value by doing the cross multiplication and division. You can throw any number you want into that if we wanted to do more, and I've got a couple of other questions in the handouts later on to practice doing that.
Ask her 2-1 or 2-0. 2-1.
Hey, Denver, I can hear you.
My apologies.
No worries. Just don't give me your banking information. Okay. percentages. We do a lot of work with percentages. And all percentages is a value of 100. And of course, 100 is the whole. So if you got 100 out of 100, you had a perfect score, whether it's on a test, whether it's in an assessment of, oh, I don't know, how efficient your operation is. The 100 represents the whole. So basically, a percent is like another way of writing either a fraction or a decimal. So the value will be the same, but how we express it will change. And what's important here is to recognize that when you are doing calculations, you may see a value of 0.12. All right, that's a decimal point. But out of 100, because we're looking at two decimal places to the left, that's 12 over 100, right, as a fraction. So they're the same value. And, you know, when we're doing disinfection, it's quite common to use, say, a 12% sodium hypochlorite solution. All right, well, we can express it in a formula or in a calculation as a 0.12, or we can express it as a fraction, as a ratio of 12 over 100. And here's some examples, pretty basic. 1 over 4 equals 2 over 8 equals 10 over 40 equals 25 over 100. So they're all the same proportion. So we can say, okay, I got one, let's see, out of a delivery of 4 valves that arrived in the stores, 1 out of 4 were in working order. 3 out of 4 had to be returned. Well, that's the same, even though there are only 4 valves. But if they say, okay, well, what was the percent out of 100%? Well, it was 25% of the valves were in working order. And again, with straightforward numbers and values, we can do that in our head quite quickly. It's the same whether the number is simple, like 1 over 4 or 2 over 8, or if it is a more complex calculation. But that's all we're doing is taking each equal sign, as you can see, going across from left to right. It's the same proportion. So ratios can be set up just like converting units. They can be set up to calculate percentages. But remember, the key when looking at percentages is what is the portion or piece and what is the total. When we're talking about out of 100%, we always know 100 is the total. So it goes in the denominator. So 12% bleach is 12 out of 100. But sometimes when we're doing meter accuracy, for instance, on a test bench, we have an accuracy of 101% because the meter is over registering. All right, so now when we're doing a calculation, we have to remember that's still the numerator. Just because it's a bigger number doesn't mean it belongs down below the line. When we're talking about percent, the whole is 100. So when we get different units and we're trying to convert across, that becomes important to remember. So always with percent, the first job is to identify what is the portion and what is the total. And then the portion always goes in the numerator, even if it doesn't make sense right away. And the total goes in the denominator. And on the second ratio, the equivalent proportion goes in the numerator and the 100 in the denominator. And here's an example. What is the percentage of 14 parts out of 50? Well, let's just set up the ratio. The first ratio comes out from the parts and totals. So 14 is the part, 50 is the whole. The second ratio is the proportion. So if 14 out of 50, what is blank over 100? Well, we know that 100 is 50 times 2, so we can probably do that in our heads, 14 times 2. But basically, this is what it looks like. Multiply the two numbers on the diagonal together, and then divide by the third number, right? So 14 equals what percent out of 50? Well, 14, we bring the 100 up to the top. 14 times 100 divided by 50 equals 28%. And remember, the proportion has to match. So if I then write it down, 14 out of 50 equals 28 over 100. Yep, that makes sense. I can see that that's consistent. If we had another example of 5 over 50, all right, 5 over 50 is what over 100? Well, 50 times 2 is 100. So 5 times 2 is 10. So we are ending up with 10 over 50, or 10 over 100. 5 over 50 is the same as 10 over 100. So that's all percent is, but it's really important that you set the question up right. So, oops, I gave it away too quickly. So sample question, 37% of 438. So now you have a different whole instead of it being 100. But remember, from the simplest to the most difficult calculation, there's always enough information to solve for the unknown. So if we scribble out, okay, 37% is really 37 over 100. So 37 over 100 equals question mark over 438. So 37 over 100 equals what over 438? So we take the 438, put it over the line, multiply it by the 37, and then divide by 100. And then the final part is 162 over 438. And you can work it backwards. So if I'm really not 100% sure that I got the right answer, 162 over 438 is what out of 100? Well, I bring the 100 up to the top of the line, multiply it by the known numerator, and divide by 438. And now I know that it matches because it equals out both ways. So it all comes down to how you set up the ratios. And for some of you, this is repeat and not new. For those of you who are not doing it very often, it's just about remembering how to set up the question to solve for the unknown. And then even if the numbers don't look like you can calculate, you never have to. You've got a calculator, you don't have to do it in your head as long as you have set it up correctly to begin with. So what is the total amount if 162 is 37%? So we know 37% is the same as 37 over 100. So 37 over 100 equals blank over 100 or 162 over blank. So we set it up the following. 37 over 100 is known. 162 over what? We then bring the 100 up, multiply, and now we're dividing by the smaller 37 value. And again, the final result would be 162 over 438 is the same as or equal to 37 over 100. So you can always double check your math by going back and seeing, okay, if I break it down and basically re-engineer this question backwards, do I get what the first question was asking me? Do I get the same amount? And the answer is yes, so you've done it right. Now, my understanding is you'll get the handouts from the EOCP or from the version of your certifying body so that you don't have to memorize. And in here are some examples that you may not be getting an exact same formula sheet, but the idea is that you don't have to memorize all of the formula. There are a couple of values that you should know, and I'll go over those. But what's following on the next slides is what you would see in BC and Yukon. Never mind how it's packaged, the formulas are what matters. So for instance, on the first page, if you look at the left-hand column, some information and constants that you need to know. Pi is 3.14. 1 BTU is 1.055 kilojoules. You don't have to memorize this. If you're writing a level 1 exam, you need to know pi. You should know KPAs. 1 PSI equals 6.895. But for the most part, you're working within metric. You're not converting back and forth between metric and imperial. So pi is necessary. These last four are good to have in your brain pan, all figured out. 1 meter of water is the same as 9.8. So a meter of water, and we're talking in height, not cubes, but the height of a column of water is the equivalent of 9.807 kPa. In terms of mass, 1 liter of water weighs 1 kilogram, and that's strict across. So it's nice when you're in metric, you have these constants that fall into multiples of 10, 100, and 1,000. So when you're working with volume calculations, especially, knowing that 1 liter of water weighs 1 kilogram, that there are 1,000 liters in a cubic meter of water. So 1,000 liters all stacked up together or poured into one container is the equivalent of a cubic meter. And if 1 kilogram of water weighs 1 kg, or 1 liter of water weighs 1 kg, 1,000 liters, not only is it a cubic meter, it weighs 1,000 kilos or 1 metric ton. Abbreviations, for some that as you move through the certification process, especially the bottom here, velocity, volume, and water horsepower are constants. If you're working on treatment, especially wastewater treatment, these abbreviations in the top half of your column are more common. Distribution system operators, not so much. Head, yes, occasionally density, flow rates, but filter backwash, so on, mostly on the treatment side of things. And then we get to the actual calculations. So if you're asked to calculate the circumference of a circle, if we look at the very top one, pi times diameter, and then how it's expressed. So C, or circumference, equals pi times d, or 2 times pi times r. And we'll talk a little bit more about the difference between using the diameter and the radius when we're doing our calculations. Perimeter, or outside of a rectangle or square, that's 2 times the length plus the width, and then how it's expressed. Perimeter equals 2 times L plus W. And you will have, for those of you writing, well, even level 2, there will be a couple of questions where you're asked to calculate how much paint you might need to paint a reservoir, the outside of a reservoir. Very important that you don't start doing a volume calculation and end up filling the reservoir with paint instead of painting the outside of it. And that's where we look at the dimensions, and we'll go into a little more detail about how important it is when you're writing down and calculating values that the units don't get lost, so that you're working with cubic meters when you need to be, as opposed to square meters, you know, when you're doing area. So the formulas that follow: area of a circle, pi, so that's the 3.14, times the radius, so r squared. You can also do pi times diameter squared divided by 4, but I think a lot of operators like using the pi r squared because it's a much more compact formula. It's totally correct. And but you might have to do a second calculation, and if the dimension that's given to you is the diameter, and we've got a couple of examples of that. Area of a rectangle, length times width. Area of a triangle, half the base times height. So those ones you will have to be able to calculate. You don't have to memorize them if you get the conversion sheets, which is good, because then you can focus on actually putting the values in the right spots when you're doing the work. Volume, important for operators to be able to calculate how much water is in a length of pipe or in a reservoir, in a tank. It's the same with wastewater operators, treatment or distribution or collection systems. So areas and volumes are critical. And the nice thing about doing volume calculations is that once you've figured out the area, then you're just adding the third dimension. So you've done the cross-sectional area of a circle, cylinder, or a square tank. So you've got the cross-sectional. It's like thinking about the tabletop. I have two dimensions, length times width, to give me the area, but that's flat as a piece of paper. And now when we're doing volume, we're looking at that third dimension, the height or depth, and that creates the volume or cubic units, cubic meters as an example. So in other words, we're now talking about filling, or how much is held within a vessel or a tank. So area, think of the two dimensions, cross section, looking at the face of a pipe in a ditch or in a process chamber. And then when we add the third dimension, we're looking at depth or height, and now square meters becomes cubic meters. So if you're calculating area, make sure you've got your square meter units, and then can add that third dimension to do volume. Rate of flow is important. You'll have to do that whether you're on the water, wastewater, treatment, or distribution side of things. And we're looking at the value of Q. And really we're looking at it. It's basically a measurement of how much or volume over per a unit of time. And in the metric world, it's usually either liters per second or cubic meters per hour. So liters is the volume, time, seconds, is how long the process that we're calculating has taken place. And then by combining those two units, volume and time, we can then calculate a flow. And then the formulas that follow, flow in an open channel for water distribution system operators typically does not apply, but on the collection side or treatment side, it does. Flow in a pipe, yes, we're looking at that. And velocity, basically, we're looking at the flow per unit of area. So we have to calculate how big an area of pipe we're working with. Detention time, typically for level 1 operators, you don't see detention time questions, but knowing the calculation and what that represents is important. So we're looking at the value dt, which is the volume of a given process divided by the flow. And of course, okay, we know that we can calculate flow by looking at the box above, and we're looking at flow being volume per unit of time, right? A times V. Okay. So lots of formula. You don't have to sweat memorizing it. If you've got these sheets and handouts, I think as we move along and we do quite a bit of math throughout the weeks that follow, you're going to get very comfortable with area. Should go back with area, length, area, volume calculations for sure. And so you can refer to the sheet, but I think most of you will be able to memorize the formula and just apply it as you see the values. We're also going to talk later on in the program as you get closer. So sort of tips about writing a test. And for those of you who have written already, you know we're looking at multiple choice. You know we're looking at 100 questions. You need to get 70 to pass, which sounds okay, but you know, a couple of missteps or looking at a question that says number 7 on the test sheet, but circling in the correct answer for number 8, you got 25% chance of getting it right. So there's some rules we'll go over a little bit more, or tips they're more like, to just feel more comfortable in the exam itself. But we're basically going to try and build your confidence to writing, whether it's a level 1 or advancing level 2, with as much confidence and not sweating the small stuff as you go into the exam itself. So we'll be doing some review, even when we're not doing math or disinfection or supply. There's lots of opportunities to talk about now I just think I just lost my chat box, so I'm hoping, oh, here we go. Okay. nothing questions. If you have any questions, please feel free to do it. I've just reopened the chat box. So if you have any questions about anything, feel free to jump in. And if I remember, I'll look at the chat box and answer you. All right. Next sheet, this is mostly going to be for treatment operators, hydraulic loading rates, overflow rates. Exception is the third box out of 4. And we will cover this off a little bit today and in disinfection in a couple of weeks. But knowing what dosage of typically chlorine we're adding water to make it effective in making the water safe for the community. So the two things that we would look at are feed rates, so liters per day, but mostly what we're looking at is dosage. So you can see in the description, amount of chlorine to be added per volume of water to be treated. So there's 2 volumes that we're actually looking at. The amount of, say, hypochlorite and the total amount of the water either in a reservoir or in a series of pipes that we have to disinfect. So that's why on the right-hand side, under formula, you'll see the volume of liquid, which is W, as opposed to the volume or weight of the disinfectant, the chlorine. So instead of 2, it is 2 volumes, but typically expressed as a weight. So we'll go through some of these examples later on today, and probably, yeah, well, not probably, definitely in the weeks to come. And then these are motor calculations typically. So we're looking at horsepower efficiencies, and the top one, wastewater sludge calculations. If you're not doing any wastewater right now, and this is wastewater treatment, then there's a whole series of calculations for calculating sludge index, food to microorganism ratios, BODs in the treatment center process, and so on. Which the formulas are there, and if you have a similar handout, and as you get closer to writing the exam, maybe you can even send me a copy of the formula sheets that you use. You can, I've told operators when you're in the exam, if it feels more comfortable, just X out the ones that you don't need to look at, because when you're looking at a lot of formulas before or while you're writing an exam, it can get a little intimidating. So, all right. So I think the, let's see, let's go on. I just got a question here that I will reply to privately. Okay, area. So let's look at a couple of simple calculations, and then we'll move into volume and dosage. Pretty straightforward. Remember, it doesn't matter how simple or complicated the problem is, there always has to be enough in the question to solve. So you might get 3 or 4 different values, but that'll be enough, even if you have to do 2 or 3 separate calculations to come up with the right answer. So sometimes they look very complex or confusing. It's just a matter of breaking it down and remember, doing the calculations in the right order. For area, it's pretty straightforward. Length times width equals A. So A is what we're solving for. All right, so they've given us length, 15 meters, width is 6. And you know what? Always on a scrap piece of paper, if it helps to draw out the problem so you can visually see what they're asking for. And what they're asking for is the shaded blue area. And so remember, that's just 2 dimensions, right? So 15 meters times 6 meters is 90 meters squared. It's always important to get the units correct. So in this case, you know, we can even just count, you know, because we're looking at 2 dimensions, meters times meters is square meters. They've given us enough information, and there's really no extra setup unless you want to draw it out. Because when we get to volume, there's a 3rd dimension that gets involved, right? For a triangle, and again, you can either have this memorized or just look at it on the sheet. A equals 1/2 base times height, where A is the area, so the shaded area, B is the base, and H is the height. All right, so 3.5 times 8 equals 28 square meters. How do we get the 3.5 meters? Well, it's 7 meters divided by 2, 1/2 base. And the one thing I don't like about this slide is it should actually have meters. 3.5 meters times 8 meters equals 28 square meters. So we're just plugging in the values. So the one extra calculation is because they don't give you the half base value, they give you the length of the base of the triangle. So now we have to divide that by 2, which is what the formula says to come up with the value of 3.5 meters. Now with circles, now we start getting into the constant of pi. And remember, you can go on YouTube if you want. There's a guy that has memorized pi's decimal places to 20,000 decimal places. It takes him like 6 hours. It takes about 6 hours for him to run the whole thing. And I'm not sure if it gives him any joy, but for some reason he has this memory that can do that. For us as operators, what we're looking at is really 2 decimal points. So you'll see quite commonly 3.14. And remember, there's no units after it. It's a constant. So there's not in meters, it's not liters, it's not grams, it's not feet, it's not inches, it's just 3.14. And that number gets plugged into any time we're dealing with a circle or a cylinder or a cone. We need to have that. So, excuse me a sec. So, one of the other pieces of working with pi is that the number value changes a little bit the more decimal points you put in, but the reality is you will be given 4 choices, A, B, C, D. One of them is going to be the closest, and depending on how the exam is set up, it might be 3 decimal places or whatever. You might have to do a bit of rounding, but it'll be very clear what is the right answer. So in this example, the shaded area is what they're asking for. How do you calculate that? Let's just say, my preference is the pi r squared formula. You can do it both ways. I like pi because once you figure out radius, it's a pretty straightforward formula. So A is the area, D is diameter, R is radius. So if I'm going to use the pi r squared, I have an extra calculation. They've given us 8 meters for the diameter. All right, so what's the radius? Well, the radius is the measurement from the midpoint of the circle to the edge. So it's half the diameter always. So if the diameter is 8, the radius has to be 4. But it's not 4 times 2, it's 4 squared. And remember our bed mass, we always do exponents before multiplication. So I am not multiplying 3.4 times 4. I'm multiplying 3.14 times 16, right? I'm going to do the 4 squared calculation first. And then we'll come up with 50.24. And remember, it's area, so it's square meters, right? So we're now looking at, okay, the cross-sectional area of the circle is all of the shaded area represents 50.24 meters squared. So we must use pi, and easy peasy, just memorize pi is 3.14 and you're golden. Bob's your uncle. All right. So, oops, I'm just doing this over again. Just, sorry, mini stroke. Here we go. Volume of a cube. So now we're going to go from area, which is the 2 dimensions, to the depth or height. So again, thinking about table or a flat surface like a reservoir, the area is length times width, which they will give you, but they're now giving you a third dimension. So in this case, 7 meters is the height. So we know length is 13 meters, width is 5 meters, but we're now looking at the third dimension. So we're just going to multiply them, and because it's all the same arithmetic function, doesn't matter the order. So V, or volume, is 7 times 13 by 5, but remember, it's 7 meters times 13 meters times 5 meters is 455 cubic meters. So we're really talking about not the outside surfaces, not flat top surfaces. We're talking about what it would take to fill that space. So if that's a reservoir or a holding tank or a wet well, that's what we're looking at in terms of the calculation. So we're adding that third dimension, which means our answer in metric is cubic meters, not square meters. So volume of a cube. Same thing, calculate the volume of an underground chamber. It doesn't matter. Again, you can draw this out, but if this was an exam question, you don't care if it's above ground or underground. You care about the numbers, right? 1.4 meter wide, 5 meters long, and 2.3 meters high. Sketch it out on a piece of scrap paper and then do the calculations afterwards to solve for the unknown. And remember, always carry your units with you, because, you know, could be a 50, 75% chance that one of those answers, A, B, C, or D, is 16 square meters. So the calculation looks good, but the units are wrong. No, it's not an area calculation, it's a volume. So you do not want to get an exam question wrong because you didn't pay attention to the units that were involved. And that's especially true if we're doing a volume, for instance, of this kind of a reservoir, and they ask you to go one extra step and say how many liters are in this reservoir. And if I look at this, I've got 16.1 cubic meters. That is correct. That is exactly the space of that cube, but it's not in liters. So if one of the answers, if A says 16.1, and I check that as the correct answer, but they're asking for it in a different set of units, then I get it wrong. Whereas, no, I have to now take that 16.1 cubic meters. We know from our formula sheets that there are 1,000 liters in every cubic meter. Oh, okay, so 16.1 cubic meters times 1,000 is 16,100 liters. And there'll be a choice there. So really critical that when you're doing an exam on any of the math questions, that you follow the units. And this is probably the most common type of level 1 volume calculation, is a cylinder. So you actually have to apply the area first. So that grayed in area at the top looks like a big biscuit of the reservoir. Calculate that area and then add the third dimension, height. So volume of a cylinder, VC, equals pi r squared times height. So the pi r squared is what you need to do to get this area, and you must do that first. All right, and if we're looking at doing the pi r squared, again, they've given us the diameter. So we have to calculate that. Our diameter is half, or our radius is half the diameter. So that's how we get to the 7, but we square it. So let's do that first. So 7 times 7 is 49. Now we multiply 3.14, which is pi, times 49. And that gives us just this area here. But they're not asking for the area, they're asking for the volume. How much is inside this cylinder? So we add this element to it, multiply 6 meters. Now we get 923 cubic meters. So the two reminders are make sure you get your units right and make sure you do the math in the right order. In this case, it's all multiplication, so that helps. The other variation of this, it says, please calculate the volume of a reservoir that is 14 meters in diameter, a 6 meter high reservoir, but it's only half full. Okay, so now I've done the math. I've come up with 923 cubic meters. That is the correct volume for the entire space. But it's not what they're asking. So by reading the question carefully, I can say, okay, 923 cubic meters is the volume of the space, but what is the volume of water if the reservoir is only half full? So in other words, 3 feet. Well, I can either scribble this out and put a 3 there, or I can now divide it by 2, right? This 3 is half of 2 to come up with the correct number. And remember, the other thing about doing a multiple choice test, for those of you who've never done one, is that the right answer is always there. It's not like you're pulling out the right answer and writing it down. It's there. So if you do the calculations correctly, you're guaranteed to find the right answer. But the two things that can trip you up every time is that you get the units wrong, or you haven't actually taken it to the next step. I want it in liters, or I'm only looking at a half full reservoir. So can't stress that enough. If you can remember that when you're doing, and we'll do some more, we'll be doing some more practice as we go week to week. But this is a key one. And here's another version of the same calculation. So for distribution system operators especially, this is critical because you often have to calculate how much volume, how much water is actually in a pipeline, either for a segment that you're going to flush or disinfect, or you're calculating how much water you've lost, along the way, you know, if you're doing leakage. So what we're really looking at is basically a reservoir like this, lying on its side. So we're going to calculate how much water is in this segment. And again, they have to give you enough information to solve the problem correctly. Whoopsie. So, how much water in liters? So here's your first clue that they're going to be asking for an extra calculation, right? Not cubic meters. And the other wrinkle is, can I ask you to mute? I'm not sure who it is, but I think it's Kenroy. Thanks. Here's the other wrinkle. Not only are they asking you for the answer in liters, but they're two different units. 300 millimeters in diameter, 872 meters long. So we need them to be the same units because you can't multiply or divide millimeters by meters. So recommend that what we'll do is convert the diameter into meters. So of course we got to move the decimal spot. So 300 millimeters is what to meters? Well, we're going to move that decimal spot 3. So we're looking at 0.3 of a meter. Now, if we're going to use this formula, pi r squared, that's not radius yet. So then we divide that, and here's where we get this number here, 0.15 meters squared. That's just this information here converted from diameter to radius. Pi we know is 3.14, but this radius value has to be squared. So 0.15 meters squared times itself, 0.15 meters squared, times pi, that gives us this information only, just the cross-sectional area. But because we're now working out of meters, we have square meters because we have area, times meters, so now we have cubic meters. That gives us this value of 61.61 cubic meters. Okay, that's the volume in this pipeline, which is great, but they're asking for it in liters. All right, so now we have to add another calculation, and that calculation is for every cubic meter in this pipeline, there are 1,000 liters. So 61.61 cubic meters times 1,000 liters gives us 61,610 liters. And guaranteed on the question on the test, there could be that answer, but with the wrong units. So you sure don't want to get a question wrong just because the units are incorrect. You will be able to use a calculator. For those of you that have written before, you know that. You can bring a calculator in. So feel free to practice all of these on your own calculator, because with the PowerPoint, it's tough to follow all the steps. But the steps are the same for volume, as this just as the same as this. The only thing is they're asking for a different result. Pi r squared times L. So pi r squared gives you this value, times L gives you this. All right, we know pi. We know our radius based on diameter, but we just want to convert this to meters, so that becomes a percentage of a meter. 300 millimeters is 0.3 of a meter. Now our units are the same, and now we can do our calculation. So half of 0.3 of a meter is 0.15. Now we do the math. 0.15 times itself times 3.15 equals, and times, sorry, 8 the length, but we get cubic meters. And again, there may be a question on the exam that stops right there. And 61.61 cubic meters is correct, you're done. But in this case, no, we got one more step to do. We have to now convert to liters. So on that very first exam sheet that I showed you here, 1 liter of water, 1 kilogram, 1 cubic meter is 1,000 liters. So if you have an exam sheet like that, you don't even have to memorize it, but you do need to do the calculation so that you get the same value is going to show up as one of your choices, right? Those are the most typical types of volume and area calculations you have to do. And sometimes they get a bit sneaky, changing it from cubic meters to liters. Sometimes they will, like in the previous problem here, you do all of the work, but they don't want the entire volume. They want a percentage of it, like half full or 3/4 full. And there's nothing stopping them from saying, oh yeah, and that 3/4 full also in liters. You know how to do the calculation because you know what the values are worth. And because the right answer is always there, it's just a matter of doing your calculations in the right orders with the units in correct representation. So when you're doing a volume, if you get square meters, you've done something wrong. You must have cubic meters for it to be a valid answer. And some of you might have found too, if you've written exams before, not every question is going to be a math question. You might leave the math questions to the end. I know some operators who have done all the math questions first just because they want, their brain is working that way and they want to get the math done. Perfect, whatever works. Just don't mismatch the answers on the answer sheet, especially if it's question number 2 and you fill it in for number 3 and then you get to 98 and realize, ah, crap, I filled out all my questions, you know, in the wrong answer, representing the wrong question. So that would be a bummer. So don't do that. All right. So here's a nasty version of the same question of this, but what they're asking is you can't have water where there's this thick lining. And you know that there are some water mains that are lined with a cement mortar, which, you know, when it was used, yeah, it takes up quite a bit of volume of space. Where I used to work, the neighboring municipality was quite a wealthy municipality. A small diameter, 4-inch, 100-millimeter cast iron mains, very old. And they got contractors in to scrape all the mains clear of tuberculation. And we'll show you pictures of all that buildup on cast iron pipe. And then they lined it with cement mortar. Well, of course, it's a uniform coat that goes all around the inside of the pipe. They actually did it a bit too thick, and they turned their 4-inch pipe into basically a 3-inch pipe. Well, now it was cleaner, probably carried more water through because of the better flow characteristics of a clean pipe, but it wasn't a 4-inch pipe anymore. So this calculation is basically, oh, okay, now I have to subtract the thickness of the coating before I do what's in the blue shaded area. So like when we were doing this one or this one, it's the same question. I have to do the area of a circle, but now I've got a pipe lining, so I have to subtract that. The trick is, though, if the cement mortar lining is 10 millimeters thick on this side, probably 10 millimeters thick on this side. So it's not 10 millimeters I have to take off, it's 20. So that's why the 150 millimeters diameter now becomes 130. All right, the calculation is still the same, and this is on this page, right? 150 millimeters minus the 20 millimeter lining gives us 130 millimeters, right? But I now need to figure out the radius. So I divide that by 2, and that gives me 65 millimeter radius. However, to solve this problem, I want to, because everything else is in meters, right, 325 meters, I need to convert 65 millimeters into meters. So we know it's a percentage or a decimal point, right? And the relationship is 1 to 1,000. All right, so we're basically moving the decimal point 1, 2, 3 spots. The quick way is 3 zeros, 3 spots to the left. So this is now our radius. Now we can work. It's the same distance, but we're expressing it as meters, not millimeters. So remember, the distance isn't changing. It's the same as when we talk about cubic meters in a reservoir or a pipe and convert it to liters. The actual quantity doesn't change, it's just how we express it. So pi r squared, and that gives us our area. So the volume is the pi r squared plus the length. So now we start plunking in the values. We know pi is 3.14. Our radius we've calculated now. We square that first, and then our length is 3.25. That final number is 4.31 cubic meters. Okay, so that's the volume. But they're asking for liters, so we're going to convert cubic meters to liters, and we get 4310. So remember, it's still 1,000, right? That's the beauty of the metric system. So 4.31 cubic meters converted to liters times 1,000 is 4,310 liters. And so now we know how much water is contained in this. And this is kind of a, not a great move to do this, but what the exam people are looking for is not only do you know how to do area and volume calculations, but as operators, this is the reality of what you're dealing with. It could be tuberculation, it could be rust buildup, it could be the cement mortar lining. Not that you would have to do it very often, but what they are testing is your competency, right? Your ability to recognize that situation. Is it a ton? No, but they still want to know. So remember, even in this question right here, 325 meters, 150 millimeter diameter with a coating of 10 millimeters. All the information you need to solve correctly is there. You know the area formula, but you have to calculate the radius. So that means taking away the lining from the total, dividing it by 2 to get radius, if that's the formula you're using, and then converting millimeters to meters. Once you've done that, now it's fill in the blanks. And then let's say you get at this point in your solving the problem, you think you're done. Go back and read the question to confirm. Now this doesn't say liters, but that's what we're solving for. Make sure that you end up with the correct units, right? The same amount of water, right? 4.31 cubic meters is the same as 4,310 liters, but only one of them will be the right answer on the exam. So make sure you don't do all that work and not get credit for the work by writing down the wrong units. Okay, hopefully that makes sense. Perimeter. Now we're looking at the outside. And for operators, they may be asked to calculate how much fencing they need to put around a reservoir or around a pump station. Or they may be calculating the outside surface areas so that they can paint them. So a perimeter is the distance around the outside. And again, it's in your formula sheets, but you know that if they give you these two, if it's a rectangle and they give you these two dimensions, you know that this other dimension will be 37 meters and this one will be 10. But we're not multiplying, we're just adding them up. So 37 plus 10 plus 37 plus 10. And because we're adding, it's not meters to the fourth power, it's just meters. 37 meters plus 10 meters is 47 meters, plus another 10 plus another 37. So that's why the units, here's a good example of why the units are so critical. Because if you did it wrong and you ended up with square meters, oh, hang on a sec. They're not asking you for the shaded area inside, they're asking you for the heavy blue line distance. And that's lineal meters, right? So in other words, it would be like measuring each dimension with string and then laying out the string. Oh, it's 94 meters long. Roll it back up and we're done. Or with a tape measure. So another good example of making sure that the units are correct for what they're asking you to solve for. And of course, if we do it for square or rectangular shaped objects or vessels, reservoirs, or buildings, the same is true for circles. And instead of doing pi r squared, when we're doing the circumference, right, of a circle, which is the same as a perimeter, but we call it the circumference of a circle, because it's the outside area, or distance, sorry, lineal distance, there are no square meters. It's single units. So that's where you see the formula. Circumference equals pi times diameter, or 2 pi r. No squaring of r, but just 2 times pi times r. So don't be confused if you're using pi r squared for area. You might want to prefer to use pi d for circumference, just to keep it different. They give you d, right, as the diameter. So circumference equals pi times d, and the units are in millimeters. So the answer is in millimeters. There's no squaring or cubing. So make sure your units are consistent. So here's an example. And this is, you may not see this on a level 1 exam, but for those of you writing level 2 water distribution, this comes up, or a version thereof comes up quite often. A steel reservoir, and again, draw a picture, requires painting to protect it from corrosion. Reservoir is 5.3 meters tall and 7.5 meters in diameter. How many cans of paint are required if one can covers 9 square meters? Okay, hang on a second. They're asking in square meters. Well, that's coverage. But our first step is we have to figure out the outside circumference of the reservoir. So note, the number of cans required can be determined by calculating the area of the sides and then dividing by the area covered by 1 can, which if you've done any projects around the house or even I don't know, baking or cooking in the kitchen, and you know that 1 can soup can fill up so much of a crock pot or a cooker. You just multiply through. So let's take this. Here's our reservoir. Draw a picture. We know that the reservoir is 5.3 and the diameter high, and that the diameter of the reservoir is 7.5 meters. We know that we'll come back to the paint can, right? But remember, because we're dealing with circumference, we don't want square meters. Think of it as taking a cut-off saw and zapping right down the side and then stretching it out so it's flat. But basically what we're looking at is the circumference, so pi d, which is pi is a constant, it's always 3.14, times the height, 7.5, or sorry, the diameter, 7.5 meters. And then we're going to add the area, because we're not just running a string line around it, we're actually going to paint it. But remember, if we end up with volume, cubic meters, that means we've figured out how much paint to put into the reservoir. Not a good idea. So the area of the outside walls of a cylinder is calculating by multiplying the circumference times the height. And the circumference, first of all, is pi times diameter. And because we're not squaring anything, it's simply the answer is in meters. Okay? So 3.14 is pi times 7.5 meters times 5.3. That gives us the area. All right, but we still don't know how many. They didn't ask us for the area. The question is how many cans of paint. So we've done everything right, and you sure don't want to see 124.8 square meters as a possible answer, because you might be tempted to fill that one in on the test. No, they're asking you how many cans of paint, right? So if one can of paint covers 9 square meters, then we say, okay, 124.8 square meters divided by 9 square meters. The square meters cancel. The number is 13.9 cans. I can't buy 0.9 of a can probably. So I'll have to buy 14 cans or get the supplier to drop off 14 cans of paint. And basically, they're asking you to show that you can demonstrate the difference between a circumference calculation, an area calculation, and a volume calculation so that you get it right. This is the bonus part. Once you get the area, figuring out how many cans it takes. Okay, but again, they've given you enough information. Once you've got 124.8 square meters as area, and you know what one can of paint will cover, now you can do the rest. So it's really looking at it sequentially. Read the question, draw a picture if that helps with the dimensions. That way you don't misplace them or put them in the wrong order, but you also make sure you carry your units with you. Okay, and we'll have a couple of examples of that to go as we go forward to do a couple more. But remember, arranging the formulas allows the formula to solve for any variable. So we're basically isolating. In other words, an equal sign, 4 is equal to 6 minus 2. And one side of the equal sign is 4, the other side is 6 minus 2. They're balanced. That's what an equal sign means. So if we know 2 out of the 3 variables, arranging the formulas is simply like what we did with percentages, moving the knowns to one side so we can solve for the unknown. That's what all this slide is saying. Moving a variable to the other side of the equal sign to isolate it. The only trick is when we do that, we reverse it. It's no longer multiplying, it's dividing, or adding versus subtraction. So a couple of examples of that. Multiplication. So A equals B times C. So let's say A is 8 equals B, which is 4, and C is 2. Straightforward. But, so how do we know what 4 is, right? If B is, when we know A is 8 and C is 2. So we move C over, and instead of multiplying, we're dividing. So basically, we're getting B all by itself and then doing what this side of the equation is asking us to do. And if I wrote in 8, 4, and 2, makes perfect sense. If I look at this and say, okay, 8 divided by 2 is 4, totally the same. So we're still in balance. Or if I want to solve for the 2, 8 over 4 is 2. So we're really just reallocating the position of the unknown to get it all by itself so that the leftover function we can solve for. Same with addition and subtraction, right? A is 8, B is 4, C is 2. I can't work anymore because we're now doing math. So 6 equals 3. That's a bad example as well. Let's do 5 equals 3 plus 2. All right. But if I want to solve for 3, well, then I have to subtract. It's no longer adding on this side. I have to move it to the other side. Same with C, right? 5 equals 3 plus 2. 5 minus 2 equals 3. 5 minus 3 equals 2. So we can do that for any variety of formulas. So here's an example. How long is a plot of land that covers 700,000 square feet and is 560 feet wide? So in other words, we've got the area already and we've got the width. Now we're solving for length. So we move L to the other side, keep it by itself. So we have to move W over here. But now instead of multiplying it, we have to divide it because it's on the other side, the opposite side of the equal sign. And now we plug in the numbers. We know 700,000 square feet is area divided by 560 feet of width. And that will tell us what L is. And we can always, when you do this on a formula or a question, any of them, you can always check your work by reversing it back. And if it still works, you're golden. Here's another example. What is the demand of chlorine on the system if the dosage rate is 4 milligrams per liter and the residual amount is measured as 0.25 milligrams per liter? So dosage is the big number, right? So dosage, CD, equals demand plus residual. All right, but they're asking us what the demand is, so I don't know what D is. All right, so the next step is to get D all by itself. So I move R over to the other side, but guess what? By moving it from this side of the equal sign, where it was an addition, now it has to be subtraction. Okay, so CD minus R equals D. Well, does that work? Well, let's see. Dosage is 4 milligrams per liter minus 0.25 milligrams is 3.75 milligrams per liter. And if I'm not 100% sure, I can reverse it. All right, do 3.75 milligrams per liter and 0.25 milligrams per liter equal 4? Yes, they do. So I've done it right. You can always flip it back and work it backwards. All right, but remember, they have to give you in every formula or question about formulas enough information to solve for the unknown. So that's 2 out of 3. So when we're doing calculations for chlorine, and typically these are the types of chlorine questions for level 1, is dosage, demand, and residual. And we'll talk a little bit more in disinfection about what those actually mean, not just the value. But dosage is how much chlorine, in this case, we're putting into a water column or water pipeline or reservoir. The demand is how much of that chemical, the organics or the temperature or the paint coatings on the reservoir wall, are extracting out of that dosage. And the residual is what's left over. And for distribution system operators, it's really important that we know what our residual is. And we can take samples. We'll talk about sampling later on. But this is the math of actually what the relationship is between dosage, demand, and residual. So they always have to give you 2 out of the 3. So in order to calculate the demand, we have to get it by itself. And this is the mathematical way of doing that. And then we plug in the values. So again, Once D is on its own, we can solve, but we have to make sure if we're going to move the residual to the other side of the equal sign, it's not addition anymore. Otherwise, it wouldn't work, right? Dosage plus residual is demand? No. The demand and the residual combined make up the dosage. Those are the two elements. It's like if you look at a clear glass container, like a test tube, and the total amount of water is in there, and half of the water is regular water and the other is oil, and you can see that clear line between them. Well, the total volume is the two values together. All right, so we move R to the other side of the equation. And so dosage minus residual equals D. And guess what? Those are the two values they've given us. 4 milligrams per liter minus 0.25. We just do the math. And that gives us our answer. So, but the principle remains the same, whether it's addition and subtraction, or in this case, multiplication, by isolating for the unknown and moving the known to the other side of the equal sign, as long as we reverse. So multiplication becomes division, or in this case, addition becomes subtraction, we can solve for the unknown. Now you might have to do some flow rates. Level 2 operators probably guaranteed to do some calculations. In the equation sheet, we looked at Q as flow equals area times velocity. Well, we've done a bunch of area. And again, typically when we're looking at circular pipe, we know area is pi r squared. So we've done that. Okay, we can just do that again. What is velocity? Well, that's the speed, right? And that's usually a function of distance over time. And then that together will give us flow. So what is discharge when a 1200 millimeter pipe is being flushed at 2.5 meters per second? And that's quite common for distribution system operators, is looking, when we're flushing, we need to know what our flow rates are. And again, they've given enough information for us to solve. We just have to take it sequentially and in the right order and follow our units. So if Q is flow equals A times V, our first step is going to be to calculate area, pi r squared. We'll come back to velocity in a minute, right? They've given us the velocity, so we don't even have to calculate it. We just stick it over here and wait. Now we do our area calculation. So remember what we did before, because we're looking at meters, we want to convert this 1200 millimeter diameter pipe into meters. So R is half, so 600 millimeters. And now we're going to move that decimal point 3 times to the left to get meters, or yeah, as a portion of meters. And now we're going to square it. Times pi times velocity. So if you've got a calculator, feel free to follow along. But what we end up with is a measurement of Q, which is the area times velocity. And we usually express it as volume over time, whereas velocity is distance over time. But this is volume, how much. And for open channel flows in stormwater or in wastewater treatment or in wastewater collection in pipes between manhole sections, we're looking at a volume, a given volume over time, how much flow is going through the system. So again, really important as you get into these calculations to make sure your units are consistent. And in this case, again, we've converted millimeters to meters. And so it's always going to be expressed as a decimal, right? And here's one where we have the flow is given to you. So Q is known. Now we're solving for velocity. Well, remember when we did this, we moved residual over to the other side of the equal sign to solve for D. Guess what? We're going to do the same thing. What is velocity when a 600 millimeter pipe is flowing at 0.3 cubic meters per second? So we know flow, 0.3 cubic meters per second. And we now have we have the diameter, so we can solve for area. So what we do is to get A over on this side, instead of multiplying, we're now dividing. All right, so now when we set this up, boom, we don't even have to think about the numbers yet. Just arranging to solve for V. So we move A over, and instead of multiplying it with V, we're dividing by, Q by A. And now we start filling in the blanks. So pi r squared is our area, which is what we're substituting here. So there's our pi, 3.14 times 0.3 meters squared. So we end up with, and then divide that by Q, and we end up with V of distance over time. And the other reason we know we're doing okay is if you look above the line, we have cubic meters. Below the line, we have square meters. Okay, we cancel, but because 3 is bigger by 1, right, we end up with 1.89 meters per second. And if we know velocity is distance over time, do our units match that? If we still somehow had square meters or cubic meters here, we've done something wrong. But square meters dividing into cubic meters leaves us with lineal meters. But the first step is always the critical one. If we're solving for V, we want to get A onto the other side. And when we do that, we have to, instead of multiply, it's now the opposite. So now we're going to divide. And now we just calculate. We've done area many times, pi r squared. We've given Q. So now it's just filling in the blanks and solving for the unknown. So practice a couple of times, even with this example, just so that you're comfortable with the calculators so that you can, work that through. Okay. And here's another version. So for the treatment operators, detention time is a standard calculation, or formulas questions around detention time. When we're doing processing, same with wastewater. There are sometimes in the distribution system, less so, but here's the formula. So same thing, detention time, how much time water remains in a tank. And when we're treating water, that becomes critical. So detention time is expressed as dt, volume of the tank divided by flow rate, because water is moving in and out. So we need to know what the flow rate is. And these are on your formula sheets as well. So example, what's the detention time? So what is dt in a tank, sedimentation tank? It holds 3.2 megaliters of water, so million liters of water. And the flow through the tank is 2,000 liters per second. So there's our velocity. There's the size of the tank. So Q equals volume of tank. So we know 3.2. That's why it's expressed this way, because it's actually 3.2 million liters. So megaliter is a shortcut. It's the same amount divided by 2,000 liters per second. So we divide this through, and then you end up with 1,600 seconds, right? Or 26.7 minutes. Okay, so you're able to do the math. dt is all by itself, but make sure your volume units are compatible before performing the calculation, right? So 3.2 megaliters, or 3200000 liters, divided by 2,000 liters per second. The liters cancel out above and below the line. 3 zeros disappear. Divide by 2 is 1,600. Now the only unit left is time, seconds. So you're not going to see 1,600 seconds as an option on the exam, but you will see some form of minutes or a percentage of hours. So make sure that your volume units are compatible, and that in both the volume and flow rate, we're expressing it in liters. So what's the flow rate? So basically taking this same formula, but now the unknown is different. So we have to change it to solve for it. So dt equals V times volume of tank over Q. So 2 steps are required to arrange the formula. Move Q over to the numerator here, right? So instead of dividing, we're now multiplying. And now we know, now we can solve for the unknown. And then we move dt over to isolate it, so it becomes a dividing. And now because we know Q, remember though, 0.35 million liters is the same as 350,000 liters divided by seconds or minutes, 60 minutes. And now we end up with liters per minute, or divide by 60 again to get 97 liters per second. So it's just a matter of arranging the formula and then plugging in the values. In this case, you don't really have any other calculations to do, as opposed to the calculation earlier here where you have to solve, you still have to calculate the area. But there's always enough information to be able to solve. And we've got some sample questions that you can practice with. But feel free using these to just continue to plug in until you're comfortable with that. Okay? I think that might be the end of, oh no, we've got density, and then I'm gonna, I think Ignatius already sent you the questions to work on, so we can start with those too. So density of water, remember in the formula sheets, 1 cubic centimeter of water weighs 1 milligram, or 1 cubic centimeter per milligram. We basically shortcut all of that to what's in bold. 1 liter of water weighs 1 kilogram, or a density of 1 kilogram per liter. So as a result, 1 cubic meter of water weighs 1,000 kilograms, or 1 metric tons has a density of 1,000 kgs per ton. So we express it this way: 1 kilogram of water per liter, 1 to 1. 1,000 grams of water per 1 liter is 1,000 to 1. 1,000,000 milligrams of water per 1 liter. But as a result, basically we shortcut it all as to 1 milligram per liter equals 1 ppm. And so you'll see them being used interchangeably. Mostly the exam questions will stick with milligrams per liter. But on this treatment side, especially, you'll see parts per million showing up much more often in terms of processes than milligrams per liter. But this is how the calculation is arrived at, so that we are confident that 1 milligram per liter is the same as, is equal to 1 part per million. And of course, when we're doing chlorination, that becomes an important foundational bit of information that we work from. So whether you're on the treatment side or in the distribution side, chlorination is critical. I mean, in this part of the world, there were no treatment plants for a long time, or it was very basic. All it was disinfection. In the Vancouver area now, the treatment plant is a full service, filtrations, sedimentation, the whole deal, and disinfection. But that wasn't always the case. But operators in distribution systems may have to apply an understanding of chlorination when either cleaning a reservoir, or repairing a broken pipe that may be contaminated, or putting a new section of pipe into service. So it's important to understand not just how the dosing equipment or treatment equipment works, but to know how to apply them in the system that you're working in. So we've already talked a little bit about dosage equals demand plus residual. The North American model has been, from the American Waterworks Association, best practice means that there is a measurable residual. So to have a measurable residual, you have to dose at a high enough value to account for the demand. And demand changes in a distribution system with the age of pipe material, the temperature of the water, and of course the amount of organics and potential bacteriological activity going on, which is why the best systems have real-time chlorine residual analyzers, so they can adjust dosage to meet demand certain times a year. We're in the winter up here, which means as we start to thaw in parts of BC that are frozen, we end up with a lot of runoff and spring freshet, which creates a high amount of turbidity at surface water systems. So that turbidity has to be accounted for, measured, and then the dosage rates typically adjusted higher in order that the demand can be met and residual is present. One of the biggest risks in the water system is if demand exceeds dosage and consumes all of the available chlorine, there's no residual, but not only that, you don't know that you've even covered off all of the necessary disinfection and potentially have pathogens in the system. In this part of the world, in Canada, 20 years ago, there was a horrible contamination event in Ontario, in a town called Walkerton, where they did not have real-time chlorine residual analyzers. In fact, one of their hypochlorinators was broken, so they were just doing a fixed dose of 0.5 milligrams per liter into the system, and contamination from surface water, a nearby farm, heavily polluted with cattle manure, got into the well, overwhelmed the disinfection, and of course there was no residual, but the demand wasn't even met. Dosage, if it had been properly monitored, could have adjusted upwards to take out the pathogenic organisms and leave a residual, but they had no clue, and as a result people died, and it becomes a horrible black mark on the water systems in this part of the world, well, Canada, because of a total failure to understand the basics. Hey, Kenroy. So, thank you. So, here's a couple. We're just dealing with the math part of it, but it's the same principle of understanding how that works. So, a chlorinator is set to dose at 5 milligrams per liter, or 5 parts per million. What's the demand if the residual is measured at 1.2? Well, remember, the dosage is the largest figure, so we know dosage is 5 milligrams per liter, but we have to solve, and using the way we've set it up, we have to get the demand by itself. So we move residual, subtract the 1.2 from the 5 milligrams per liter, and the demand is 3.8. Remember, we can always check it by going back the other way, moving the values to the other side and coming to the same answer, right? So 5 milligrams per liter is the dosage, CD, minus 1.2 milligrams per liter will give us the demand. So this will show up quite a common calculation to be done for level 2 operators and level 1 treatment operators. There might be the odd time this shows up for level 1, but mostly it's a level 2. But same formula, but now what we're looking at is treating a volume of water over a period of time. So CD is the dosage, but now we're looking at solving for the amount of chemical we need, say sodium hypochlorite, over the total volume of water, either in a tank or moving through a pipeline. So this is how that formula is set up. And you don't have to memorize it because it'll be in your formula sheets. But recognize that we're looking at dosage on one side is equal to how much in kilograms of chemical we're adding, times 1,000, that's the constant, over the volume of water in cubic meters. So let's use an example. And then I think we're almost done because your brains will be full. But anyway, so what's the dosage? So what is CD at the chlorination station when 17 kilograms of chemical has been used? So we're looking for the big number, CD. When 17 kgs or kilograms of chemical has been used to treat 3,000 cubic meter of water in 24 hours. Well, this formula, you don't have to worry about inserting time in here. You're just looking at the weight, which is 17 kgs times 1,000, divided by 3,000 cubic meters. All right, and then by calculating that 17 kilograms times 1,000 divided by 3,000, we end up with 5.7 milligrams per liter. All right, so we now know the dosage rate at the station, okay? And a lot of times we're looking at the readings on a cylinder or a hypochlorinator, and we can check the volume, and we just want to double check on the dosage rate based on the known volume of water that passes through or across that hypochlorinator. Now here's one where basically the reverse. We've been given a dosage and we have the volume. We just want to know how much in kgs was added. So remember, we want to isolate that. So we move the volume over to the other side, and because it used to be divided, we now multiply, and we're now multiplying the 1,000, so we divide. So it ends up looking this way, again, following our formula for arranging to solve for the unknown. Because we know what CD is. We just plunk in our numbers. So 4 milligrams per liter is our dosage, our total volume of liters here, but we're converting it to cubic meters. So 45 million liters is the same as 45,000 cubic meters. Multiply that, divide by 1,000, gives us our unknown. So remember, we've been rearranging the formulas to solve for the unknown, and as long as you say, okay, that's the only one value I don't know is weight, I have to get it by itself. So I got to get rid of the 1,000. Well, if I multiply it, now it's divide, so it's below the line. Okay, I got to get rid of this and put it on this side. I know it was divided. Well, I got to multiply, so it goes on top. So you never have to guess where everything goes. Now we throw in the numbers and do the math, do the arithmetic to follow. So practice it a couple of times with a calculator just to get the feel of it. But if you are confident about solving for the unknown, it takes the guesswork out of it. Okay, I've written out the formula. I know CD is all by itself over here, but I already know it's 4 milligrams per liter. And I already know volume W is 45 million liters or 45,000 cubic meters. But I need to get this all by itself, all right? 1,000 was multiplied, so it's got to be divide. The 45,000 cubic meters was divide, so it's got to be multiplied. And then do the math, and you never go wrong. And because you're doing a multiple choice, the right answer is going to be there. But remember, there are a couple of little things that have been thrown at you is 45 million liters, convert that to cubic meters. So you'll be given enough information to solve. This is a great way of laying out the formula. So the other thing is they'll give you the formula. So once you plunk in the values, say, okay, I got to get the unknown all by itself. Flip it to the other side of the equal sign and then do the opposite. If it was multiplication, we're going to divide. If it was addition, we're going to subtract. So you can play around with that. Here, how much water was treated. Now they give you the weight and they give you the dosage. So it's just the volume we don't know. All right, so to get the volume by itself, we've got to move the dosage. We're going to divide that, right? We cross divide. So now we plunk in the numbers, 16 kilograms times 1,000 divided by 3.2 milligrams per liter. And remember, with these kinds of questions, because whether it's the dosage and demand and residual or these with the weight of chemical, you can always reverse engineer it and say, okay, if I'm not 100% sure, does it balance out right if I plug it in the way the formula is given to me on the formula sheets? And if the answer is yes, you've done it right. Last one, I think. What's the chlorine dosage? And here's the one where it's that piece of pipe again. So now we have to do all of that 300-meter section of 200-millimeter diameter water main treated with a 12% bleach. All right, so we lay it all out. And then looking at the concentration times the volume of liters. Remember, the concentration of liters, 4 liters of 12%, that's how we get the 0.12. That's the same as 12%, or 12 over 100 is the same as 0.12, right? Times 4 liters, times 1,000. The 9.42 is our calculation here, cubic meters of volume. And that's all we're doing is calculating, like we go back to the area of a cross-sectional area of a pipe times length. So it's an area and then a volume calculation, pi r squared times height or length. That gives us this number here. So we had a couple of calculations to do. It doesn't matter which order you do them because you can't solve for the final value until you have all of the elements worked out. Okay, you got to figure out what the volume is. We've got to figure out what the 12% bleach of 4 liters of bleach is worth. Just express the 12% as a decimal and then calculate it through. And once you get your final number, plug it in over on the other side, 51.0 milligrams per liter. And if it works out going the other way, you've calculated correctly. Same thing, 12% sodium hypochlorite is to disinfect the 300 meters. We're again solving for the 4 liters because we've been given the other parts, right? We've been given the 51 milligrams per liters. So now we arrange the formula to solve for the amount of bleach. So volume in the tank, cubic meters times the dosage in milligrams per liter divided by the concentration over, or times 1,000. Volume is still the same, 9.42 cubic meters. It's just where we put it, on above or below the line. So my recommendation is do it a couple of times yourself with the calculators, even when you know what the answer is, and just be comfortable in solving for that. Oh, that is the last one. So, but the formula or the theory behind it is still the same, right? We're looking at isolating the unknown on the other side of the equal sign. As long as we do the opposite, when we move something from one side to the other, we can then plug in the numbers and solve. So that's the end of the math section. Now I know I had a handout. I think there was a handout given to you. So let's share that. I believe it's this one. I think you have this. And a lot of this is review. And actually, we don't even go into the dosage. This is more for the distribution people, not the treatment people. So if you're working on the treatment side of things, feel free to do it. There'll be a different instructor for treatment than distribution. But what I'll do next week, same time, as Ignatius said, we're looking at 3 o'clock your time next Wednesday. What we'll do to start with is go through the assignment, and that'll I'll bring up the PowerPoint again, and we can go back to those parts of it. And then what I'd like to do is move on to hydraulics, which is math in a way, but basically the application of certain formulas to how the distribution system works. So that's basically it for the day. I know it's 5 o'clock your time now, so I will set you free. You're done. We will see you next week.
Thank you, Mike, and thank you everyone for joining. I've been recording this, so for those, I think there's some people send us emails at the last minute. They were still tied up in the field, so we're going to share with them. But please do send us an email to say which cohort, whether you're following water treatment or water distribution. We didn't quite have that from your utilities, so please send us an email. I've given you my email contact, or you can send it to Ms. S. Joseph, Susan Joseph at CAWASA.org. Okay, so I'll be sharing with you the recording for those of you, just as a refresher, and we're going to keep it for those who missed the program. So thank you very much. Mike, should I send the link for next week? Because what I'm trying to do as well is to keep the register of the participants. If I don't know which way you want to do it, and if I record it,
I think that's, yeah, I mean, if that worked okay to make me co-host, I would prefer that as well. That way you've got a record of people registering and updating your end of things, if that's okay.
Yeah. Excellent. Yeah, because we need to keep track, because we got to report to the various HR managers of your participation.
Right.
Yeah. And
Fair
of
enough.
course, your credits will add up to your credits for CEUs. So that's important that we can track it.
Right.
Okay. All right. Thank you very much.
So same time next week then.
Yeah. Cheers. Bye-bye.
All right. Thanks, everyone.